Welcome everyone to another session in the DataHour series. We are excited that you have joined us online this evening for an interactive session. I'm Raksha Nagaria, part of the data science team at Analytics Vidhya, and I will be the moderator of this session. And for those who have joined us for the first time, a brief introduction about this DataHour session. The DataHour, it's a series of sessions conducted by Analytics Vidhya, led by top industry experts. And it is a fun way to understand the concepts of data science from the leading players in the data tech domain. And as the name suggests, it's 1 hour dedicated to data. And we are hopeful that these sessions are going to be a great source of enrichment and value adding for your community members. So now on to our session today, which is interpretable machine learning. Interpretable machine learning is needed because machine learning by itself is incomplete as a solution. And the complex problems we solve with machine learning are not solvable through conventional software engineering. By explaining a model's decisions, we can cover gaps in our understanding of the problem and its corresponding solution. Black box machine learning models are thought to be impenetrable. However, with inputs and outputs alone, a lot can be learned about the reasoning behind their predictions. In this data hour, we will cover the importance of model interpretation and explain various methods and their classifications, including feature importance, feature summary, and local explanations using Python. Now, onto our speaker in this session of data hour, we have Serge Massis with us. He has been at the confluence of internet application development and analytics for the last 2 decades. Currently, he is a climate and agronomic data scientist at Syngenta, a leading agribusiness company with a mission to improve global food security, having lengthy background in entrepreneurship and web development. He's the author of the best-selling book, Interpretable Machine Learning with Python. He's passionate about machine learning, interpretability, responsible AI, behavioral economics, and causal inference. So over to you, Serge. The virtual stage is all yours.
Hi, everybody. Just make sure that everybody got the link for this notebook. So I'm just gonna leave it here. It's very simple. And so everybody can access it before I start going through it. If not, just scroll back in the chat. It's there several times. I've also posted a link to the GitHub for those that wanna get the actual Python, the Jupyter file from there and all that, and install it in their machine. But it's probably going to take a while. So for the sake of expediency, I hope everybody uses Colab, and then later on they can try doing it with their own local environment or some other environment. Okay, so without further ado, I'm going to go head on in the code. And as I go into the code, I'm going to be explaining a few concepts. So the first thing to do is, it's going to say, it's going to show a warning, so you know, because even though I did author this notebook, I didn't do it with this account that I'm connected to right now. So it's going to tell me that. Well, it's going to tell you that too. And so, you know, it's going to install all these things. And then once it's done, it's going to ask me to restart. And thank you for joining this session. This is going to take a little bit, but, you know, that's what usually happens. I'm going to scroll forward and explain some of the libraries here as is installing them. We're using a library called Folk Tables, which includes census data from the US. So it includes all kinds of census data. So we're also going to use Scikit-Learn. For those who have been in the field even a little bit, you've probably seen this library. We're going to use it to train test, split the data, as well as a few other things like making a pipeline, scaling, and then a lot of the models come from there. But that's also the case. We're also using CatBoost. It's a very good ensembled tree-based model. And then one called, a few that you might have not heard about, rule fit. figs, and explainable boosting classifier. And I'll explain further on why we're using those. And then, well, again, another very common library, matplotlib. And then Seaborn is a very good add-on or replacement to matplotlib. So I highly recommend that. Um, and then also, you probably, if you heard anything about it, explainable AI or interpretable machine learning, you probably heard of CHAP. We're also importing CHAP. There's a library called PDP plot, PDP box, PyLAL, and Lime. Lime is also very well known in this area of explainable AI or interpretable machine learning. Um, so let's see how this is going. Yeah, it's almost done. It takes a while. It will show a few errors, and that's okay. So I restarted the runtime as it asked me to. Now I'm ready to go. So first, it's also so you know it's going to show a few deprecation errors. They're, sometimes during the year they're very common because there's new releases of NumPy or one of these base libraries, SciPy or even Pandas, and so they make everything else kind of, show these errors for a bit. The next thing we're going to do is load the data set. So these two lines alone are going to grab census data for 1 year and then subset the data for one state. I'm using North Carolina, which is my uh, home state. So you could use any other state, but we're going to use that. There's a few pre-processing steps I'm going to do. We're only interested in a few features, so it's going to subset by those features. It's going to fill the NaN with 0 and then convert everything to integer because all the fields um, are discrete. Then the other thing we're going to do is we're going to age of all the folks are 16 and above. And I probably should have started with this, but as it says right here, we're going to be creating an unemployment classifier. So we're going to try to classify if someone is unemployed or not. Probably technically unemployment is not the right term. We're just figuring out if they're working or not, because unemployment is technically people that are looking for a job and don't have one. But these are people that are not working, whether they want to or not. And then we're also going to convert some of these fields that were encoded as 1 and 2 to 1 and 0, so they're binary, just a lot simpler to understand. And then finally, this is the target variable, which is the employment one. And where it used to be categorical, where it has all the categories. If they're military and they're working, if they're not military and they are working, and so on. There's just a bunch of different categories. We're only interested in the ones where we're only interested in these over here. Yeah. So we're gonna run that and this. And so here you see what are all these different columns. I'm going to explain them in a bit, very quickly. So this is a very simple way to figure out what's in your data set. So as you said, there's everything is, all the values here that say non-null match this one, meaning that they're all non-null. All the values are filled, and it's all discrete. So that's good. And if you want to just verify what's in there, you can just go sample and do the choose a random sample. Just to explain this, it's always good to have a data dictionary, or at least find one. In this case, I had to find one and fill this in for you guys. And so it shows here the age of the person, the schooling, the marital status, the categorical, the relationship of the person, if they're the spouse or the biological child of the person that is in the house, then the disability status of the person, and then the employment status of their parents, their citizen, if they're military, if they have moved recently, uh, uh, ancestry of the person, if they were born there or they're born elsewhere, and just a bunch of different ones. If you want more details about this data set or collection of data sets, you can look at the GitHub repo here or go to the paper they wrote. Some people say it's too small, so I'm gonna zoom the screen. Is this better? I hope it is. All right, so the next thing we're gonna do is gonna figure out how many are not working. Um, then we're gonna define a seed for reproducibility, then define an X and a Y with the classes, and then we'll quickly train 10 models. So this is here we're just initializing all these different models. So we have logistic regression, naive Bayes, k nearest neighbors, decision trees, and then a few you might not have heard of, but I'll explain. Figs, rule fit, EBM, explainable boosting classifier, random forest, cat boost, MLP. This is a neural network, just a vanilla neural network. Just a couple of disclaimers, no hyperparameter tuning, since I've already predetermined some good hyperparameters. And it's highly recommended to evaluate on stratified k-fold cross-validation, but we won't have time to do that now. In any case, the results won't be too far from the CV averages, so you know. So this is gonna take like probably like a minute and a half. Uh, Someone is asking why we're using XGBoost. Yeah, because CapBoost performs better in this case. That's all. I tried XGBoost and CapBoost performed better, and that's sometimes the case. Like there's um, four like possible or very well known alternatives to XGBoost. No, three. There's CapBoost, like GBM, and then there's the ones that come in Scikit-Learn, and you never know which one will do better. Honestly, it's not great to have a go-to. In any case, there's depending on the problem, there might be good reasons to use CapBoost. In this case, CapBoost, as the name says, is good. When you have a lot of categorical features, and that happens to be the case. So I'm not surprised that CapBoost did better than XGBoost in this case because it's a model that pretty much was designed for this kind of problem. And someone else asked, why are we checking imbalance? Imbalance is a very important thing to check before you train a binary classifier because you might have to tweak some things here. As you see here, I use some in my parameters. I use some things to kind of counter that. So you see class weight balanced. Um, it's a good idea to usually include it unless you're like 50-50. Although it's not sometimes a guarantee. And sometimes you have to, like in this case, kind of push it in a different direction just to make sure that it has the right mix. So this is another parameter that helps with that in CatBoost case. So now we're going to compare the models. So what I did here is I just put the dictionary produced by this process over here into a data frame, and then I did some kind of styling to it. So you see, I'm only interested in the top four, let's say, in every metric. So I'm highlighting the top four in every metric, and then just bolding the top one. So I can color, by the color, see which ones were better, which ones were slightly worse, and so forth. So Usually, this is the extent of all model interpretation performed, um, and that's a shame. Solely for model selection purposes, which is like piloting an old-fashioned plane with a half dozen instruments, and then like it's an approach that might work under perfect conditions, but you have bad conditions, and you're piloting a plane like this. I mean, you're going to run into trouble, right? It's not very robust. Indeed, interpretable machine learning or explainable AI is the collection of tools to effectively pilot AI or ML. I believe so because, like data conditions aren't always ideal. So which plane would you rather pilot or be a passenger in? Be honest, left or right? Uh, I mean, I would always go with right. I mean, I believe just as in additional instrumentation in planes make flying safer, additional instrumentation in machine learning can make predictive modeling fairer, more robust, and overall more trustworthy. And I'm just going to provide a little example of what can be done. Just going down this rabbit hole of predictive performance, because predictive performance doesn't stop here. This is a measure of how much error or the contrary of error there is in a data in a model. And what is actually very useful is to kind of dig deep into it to see how the model error can impact reliability, safety, and fairness. There's a This is a very broad topic. There's there's great tools for it. I highly recommend Microsoft's open source error analysis tool. We won't use it here. I mean, it can really dig deep into things. As you can see here, you can break down error in so many different ways. But I will provide a quick example how error distribution can impact outcomes. First, in order to simplify comparing cohorts, I'm going to translate encoded categories into labels. Um, so here's like the meaning of each one. And then I'm gonna, and these are just simple functions that they group the data frame by a variable and then compute predictive performance metrics for that group alone. So here I'm gonna do the error breakdown by race. So you see how it's broken down by race. As you can see, one race tops most metrics. That's not very surprising. This one might top a few, but that's obviously like that's why balance is such an important question in machine learning. You might not know if this is enough to actually make a very good um, you know make the model learn better about the distributions in this group. Okay, and so here's another one by sex, and you can see, not surprisingly, uh, male does better in all the metrics you see here. Okay, there's a whole host of tools used to quantify bias and mitigate it, and for that, I recommend the AI Fairness 360. Here's a link to it. That's not the focus of this session, but to start to understand models starts with the foundation. And so here you see fairness, accountability, and transparency. I like to see it as a pyramid where transparency is actually at the bottom. And so all of these things together equals trust. It's not there just for like ethics and like be able to say, oh, okay, our product is ethical. No, it's also good for business objectives to have and a product that is trustworthy, that you can understand how the outcomes are made and so forth. So let's dig deeper. So this section is about learning how the model works, or at least interpretation, how it's arriving to its predictions. Let me see. Oh yeah, I reran that. So you might have heard of the concepts white box model and black box model. what I'm saying here is that on one hand, black box models are too complex to make sense, but white box are privileged because they have simple mechanisms. Um, for the former, we can use something called model-specific methods, and for the latter, it's mostly, but not entirely, model-agnostic methods that are used to understand it. So first, we're going to go to the model-specific versions, which invariably use intrinsic parameters. In other words, they kind of like take apart the mechanisms to understand it, and they're not treating it as like if it was completely sealed and you couldn't see the insides. So for logistic regression, like all generalized linear models, has a mathematical formula. And if you've taken an applied statistics course, or even just a statistics course or statistical learning course, you've probably seen this before. The B's are the betas are the coefficients, and the beta zero, the beta naught, is intercept. So if you wanted to, you could reconstruct the formula from the model. You could start extracting the coefficients and intercept like this, and the rest is just simply some math and simple math like a dot product, and there you go. Yeah, typically, although you see this like this, it's done all with linear algebra. So yeah, it's the foundation of a neural network is just this with like a nonlinear function in several layers. So here we can look to understand, it's although it's helpful to understand the math, it's probably more important to understand what matters most to the model. Fortunately, since the features have already been standardized in the Scikit-Learn pipeline, the coefficients already tell us the story. All we have to take is the absolute value and rank them. So all I'm doing here is creating a data frame with the feature names and the coefficients, well, the absolute values of the coefficients, and then sorting them. And then, we style it, and here you go. So this is all the coefficients. As you can see, age is at the top. RELP, I forgot what RELP was. We can scroll up and look at what was RELP? The relationship and disability. Yeah. So they're just who are they in the household? That's what it's saying. Okay. Another model that has the coefficients can be understood as part of a mathematical formula is naive Bayes. We won't get into details because that would just make things too lengthy here. On the other hand, another interesting one is k-nearest neighbors, which cannot be understood as a mathematical formula upon training, because all the model is training data. What k-nearest neighbors does is that it stores the training data, and then when it needs to do the prediction, it just looks for the closest points in the training data to the instance you want to predict for, and then it chooses like the median or the average or some kind of measure, to come up with in this case, since it's a classification problem, it's taking the 7 closest points, and then it's taking the mode, and that's the one it's predicting for. So it can important factors coming to also the distance, because when it's taking the 7 closest points, you have to say, okay, what do you mean by closest? So distance is a very important parameter for k-nearest neighbors. But yeah, it's a very simple thing to understand upon inference, k-nearest neighbors. And training, there's pretty much no training. It's just saving a data set. So a decision tree is one of the most intuitive models to understand. Our model only has a depth of 3, which makes it even easier. Obviously, if you have a decision tree with a depth of 10, you're not going to be able to understand it easily. So here it can be easily understood as this. If you're younger than 62.5, then go here. Otherwise, go here, and then it ends up eventually picking a class. So we can plot a graph with the tree too for even more details. So this is how it looks once we plot it. See, so here you see the 8 leaves. This is where it ends up making the predictions, just as it was here. This is just a different kind of visual, uh, a different presentation of it. So as you can see, each one of these has a Gini coefficient, which is a measure of impurity. So it just tells you, how effective it is in kind of discriminating. And you can use this to tally what is the most important features. So here we can just show them by importance, and it shouldn't be a surprise that you see a bunch of these with 0 importance. Why do they have 0 importance? Well, if you take a closer look, there are only 3 features in the tree, yet it does a fairly good job at predicting with just 3 features. So you don't necessarily need a lot of features to make a good prediction. You need what the model needs. um, so this is a new interpretable tree-based model, which is very promising. It's called Fast Interpretable Greedy Tree Sums. It just came out this year. Very exciting. You can see the paper about it here. And all it is just, this is a card tree like the one we just saw. It's a single tree, just branches out. And R happens to be symmetrical, but they're not always the case. Sometimes you have it all kind of slanted in one direction or another. And so in Fig's case, what happens is that Fig's happens to construct several trees, and there's just an addition involved. So at the end of each leaf, there's a score or a probability, and what it does is it just adds up the probability from one tree to the other and so forth. So we can just simply look at our fixed tree like this, and this is our fixed tree. There's actually 2 trees, so tree 0, tree 1, and this is what happens. So if we wanted to understand a prediction, we could easily do it like this. As for rule fit, what it does is extract rules from graded boosted decision tree and converts them into a binary feature. So just imagine if you had a rule, and a rule would be not a single feature, but well, it could be a single feature, but it would be like this feature is greater than this number, or equals, or it equals this number. And then it could be joined to another one. So it would be, A is greater than 0 and B is greater than 5. So that would be a rule. So then what it does, it fits a regularized logistic regression model to the rules, and optionally to the original features themselves. So here you can see the paper about it, and you can extract the rule fit rules coefficients and intercept like this. So you can see there's 29 coefficients, but only 13 rules. The difference is due to 16 coefficients belonging to the original features. You can also use, so you can see what I'm talking about. You can use the get rules function to the data frame with all the model details. So here I'm just gonna pretty it up, but all it is a data frame. So so this is a rule. This is the most important rule. This is its coefficient, and support is just how many training, what percentage of all the training data ended up relying on this. So it's a kind of, this is really a, how do you call it? I don't know exactly how the authors of this calculated this, but I don't think it's weighted in accordance to the support. It's just not weighted according to that. But it's here you can see another rule and its coefficient. And so all of this, the reason you see coefficients is just it's a logistic regression model. So these coefficients correspond to the logistic regression coefficients. Yes, I just got a question about that. They're just interpretable in the same way logistic regression coefficients are. So here you'll see the support, and the support is important because every original feature like this one that is not a rule, in other words, um, has 100% support because it was basically based off um, the training of the entire feature, or it's supported by all the all the observations, whereas a rule may only apply to a fraction of all the observations. Okay. Um, as for explainable boosting machines, gets a little bit more complicated, but an easy way to understand it, it's like a linear model, but it's a linear model where every feature is isolated in a function. So you have instead of a beta times a number, you have a function, and that function could be anything. And so the importance of this is that pretty much every feature is separable, and that's important to have. When you have every feature being separable, it's easy to understand. And so I won't get into too many details of how this works, but there's a link here, and it will take you to an explanation of that. Well, to understand it, it comes with a dashboard. And this dashboard calculates importance, using the intrinsic parameters of the explainable boosting machines. So here, this is just a feature importance. So we've covered a lot of different models, or at least mentioned them. But what to do with random forest, cat boost, and MLP? Um, the only thing to do with those is use model agnostic methods, which treat the models as a black box, also known as post hoc interpretability. So first for the cat boost, and you could do the same for the random forest, where we're going to create an explainer. Then we're going to extract the shaft values from the explainer. We're going to verify that it is a right explainer. Someone is asking what if MLP is. MLP is a neural network. It's a very simple neural network, a vanilla neural network. So here we can verify it's a right explainer because there's different kinds of explainers between SHAP, and this method will automatically choose which one. Want to make sure it's using the tree method. And so we can do the same for MLP since it uses the kernel explainer. It takes much longer, so we're not going to extract the SHAP values from it, but we can at least do that, and then it's gonna be able to show this. So I've commented out this line, which is the one that takes the most. And then for the cat boost SHAP, it's going to return two different values. I mean, it has this attribute values and this one data. And you can see that both have the same shape. Someone's asking about the kernel explainer. The kernel explainer only applies to to models that aren't linear or tree-based models, pretty much. If it's a deep learning model, this method might be able to find something for it. Like there's several specific ones to deep learning, but they're precisely kind of a tweak for convolutional neural nets and that sort of thing. For this one, the only option we have is the kernel explainer, which is doesn't leverage at all. Actually, I have to kind of as a disclaimer, SHAP is model agnostic with an asterisk. This this tree-based explainer actually cheats a little bit. It does use the intrinsic parameters, and that's why it's so much quicker. The kernel explainer, on the other hand, is truly model agnostic, but it takes a lot of time. So we're using, for the sake of expediency, we're using, actually, although this says model agnostic, we're using a model specific one. So the first thing we can do with the SHAP values is this. Just a simple bar plot with our feature importance values, which in this case are like averages of the absolute value of the SHAP values. That's what they are. Someone's asking, does SHAP show correlation, causation? No, only correlation. If you wanted causation, you would have to use another method. You would have to use maybe the causal discovery methods. There's plenty of causal discovery methods, like such as PC. But I mean, I wouldn't, and then that's only on the data. For the model alone, you would have to use like a causal model to come up with that. And causal models typically have coefficients you can interpret. So here are the bar charts with the feature importance split by cohorts. So this is another thing. You can take this like this, but this is just an average. This is just an average, but it's not like it is for every instance. So you can split it up many ways, and this is an example of how we can split it up. We can split it up between white and not white and see what the differences are. You know, how in this case, age is a bigger factor for white folks than it is for black folks. But disability is a bigger issue for, I mean, not white folks. I said black, but not white, I mean. You've probably seen this plot before, which is called a B-swarm plot. This is a very good way of, at a glance, looking at the SHAP values and understanding them. So what we see here is very similar. It's ranked the same way the bar plot is. So all the features are ranked by overall importance, but the way you visualize this is different in the sense that you can tell what values, what feature values, whether high, low, or middle, are on each side. So if this is the dividing line between being in the positive class and being in the negative class, you see which values correlate the most with each side. So you can see higher values of age correlate negatively and the lower values of age. And then so forth. You can see it split up on what it is on each case. Oh, I think it's the other way around. Oh, I know why it's the other way around. Okay, there's a reason for that because our predictor. Okay, so if we go, let me see this model. I'll quickly explain that because this is an important concept. So if I take this and I go predict proba, which is the one that gives us the probability, and we go X test, right? See, it shows two values, right? The first value is the negative class. The second value is the positive one. So one of the things that sometimes happens with SHAP and a lot of different interpretation methods is they'll take the first number because they assume it's only giving you the negative one. So there's ways around it, but I didn't catch this one on time, so I'm sorry about that. So actually, this has to be interpreted the other way around. So anyway, the partial dependence plots don't have that problem. So these are like global ways. These are like general ways of seeing, understanding your model. So this is a global interpretation method, but precisely one that involves all the features at once. Here we can look at features one by one. So these are called feature summary explanations. And one of the most important ones is, partial dependence plots or something like that. So with the partial dependence plot, it pretty much takes what you see here and you can see it like more closely. and with much more detail. So you can see here, well, the lower the age, low age means low likelihood of being unemployed, and then it increases, and then um, hold on. Again, this is also a flip of this been flipped as well. All right. Well, but you see what I'm saying here. It actually, if you see this the other way around, um, if we can see this as being an increase in the probability of being employed, and then a decrease in the probability of being employed when you're over this age, and so on. So here we can see another one. This is closer to the PDP single feature one. So this is the SHAP version of the partial dependence plot, and this is a different version. I like the PDP box version because it's a little bit more detailed. Here you can see some confidence intervals. You see also, instead of you seeing this histogram here, you can see this distribution. It's fairly well distributed. But perhaps the best thing I like about the PDP box one is the ability to show the ICE plots as well. So here you can see the ICE plot. Yeah, someone's asking about the coefficients in linear regression. Yeah, everything is machine learning are correlation machines. So anything you ever see are correlations. And what if your feature was not categorical? This feature is an orthogonal feature. For categorical features, it's kind of tough to see partial dependence plots because like there's not enough values or range of values to make a lot of determinations. They make for very boring partial dependence plots, but PDP box has a method for them when you have a binary features or categorical features. So this is for schooling, for instance. This is what schooling looks like. So I probably should explain what the ICE plots mean. So what partial dependence plots do at the core is they say, okay, what if? So they take every single observation and change the value to every single possible value. So for every single observation, it said, okay, what if the age was 16? What if it was 22? What if it was 31? What if it was 39? What if it was 46? And then it sees what output the model does. So then the PDP line, this one in the center, is actually the average of all these different possibilities. But these lines you see is where that average came from, which was permuting every single observation to have every single value. um, so it just basically gives you an idea of what kind of trends you can see there. So I rather like it, but it has a number of flaws. The way it assumes that every single value is possible, and that might not be possible in terms of distribution. So like some of these things might be unintuitive. There might be cases in where it's saying, okay, well, what if a 16-year-old had a, what if this observation, which is of a 39-year-old, and has a PhD, what if it was 16-year-old? And then you're like, well, there's not a lot of 16-year-old with PhDs, so this doesn't make a lot of sense. So that's why PDP is not such a great for everything, especially if there's a lot of interaction between the features. But in this case, ALE is a lot better. I won't get into a lot of details, but ALE will give you a better understanding of, and it will kind of control for those multicollinearity a lot better. So it's like a PDP plot, but better, basically. SHAP has something very similar, which is not the partial dependence plot, but it looks very similar. It's called the scatter plot. So the scatter plot just scatters the SHAP values for a specific feature across all its different values. So one of the cool things it can do is it can it can also color code them in accordance to another feature. And so that's what I'm doing here. So you can see how some are lower values of schooling are, there's only lower values of schooling, of course, when you're young. And then these different values, they kind of employment, as employment increases or the possibility of employment, um, you also get some kind of pattern here between how the schooling, interacts with that feature. It's kind of subtle, but you see lower schooling, of course, kind of be on the lower end of possibility for employment in every instance here. And then up here, it kind of flips. So the lower schooling you have, the higher probability that you're employed up to an older age. So see that that's a very interesting dynamic over there. So here we're going to do something interesting. We're going to take the SHAP and we're going to do some clustering. So this takes a little bit. Let me see how long it takes. No, it didn't tell me. Oh, never mind. So, well, in case you didn't know, a nice way to figure out how long your cells take in running, you just put this at the beginning, and it will show you when it's finished. So next time I look at it, I'm like, oh, it took like 2 minutes. I can run it. um, anyway, so I'm gonna run this later, but this is what shows up. So you see which features are clustered the most. So age is clustered with MAR. I forget what MAR was. Let me go back to the data dictionary. MER, marital status. So age and marital status, of course, they're connected. And disability in general, and then I think a DREM is hearing difficulty. So disability and hearing difficulty, of course, and military, if the person is military, and ESP, which one was ESP? Um, employment status of parents. So yeah, that makes sense too. So whether the parents are employed and then whether they're in the military have something to do with each other. So here we can see using chat what kind of connection there is between all the different features. See, it took 49 seconds. Um, and this is a very high cutoff. If you then later look at this clustering over here, you realize that this is just I think an array. These are the clustering values over here. They're very high actually. Um, so for the most part, so you can tell that there isn't a lot going on in terms of interaction in these features. Not all of them are interacting, which is a good thing. It makes it everything a lot easier to understand. So we're going to take two of the features which don't interact a lot, but they're ordinal, so it makes it a lot easier to look at these plots, 2D plots. So that's why I chose them. Um, so this is a 2D AL plot, and you can see the effect on the prediction based on where they are. And you can do the same with the PDP plot for the very same features. And you see they have a connection here. If you look at the colors, the brighter colors are over here, except for this corner over here. So yeah, they have some connection, but I would trust the AL plot a lot more. So something to note is that we can always verify um, these plots because we have to wonder where does this come from? Where did the model learn this? And we can then look at the data. Well, firstly, this is looking at the data. So let's look at the data with this plot. See, so the darker colors over here are on this end. If age is over here and schooling is over here, age and schooling, darker colors. Yeah. I mean, in this case, it's darker. In this case, it's lighter, but it's basically the same possibility. Like what this is doing over here is it's averaging all the target variable or the labels. So this is based on the labels, and then it's just averaging them on different cohorts. So this is cohorts based on age, and these are cohorts based on schooling. And so these are the averages, and this is the amount of the size is the amount of observations in each cohort, or subgroup or whatever you want to call it. So you can see that is where this is coming from. This is where the median prediction is coming from over here. They're not actually averages. I think they're medians. No, this is an average. This is a median. Okay, so here's another interesting difference over here. This is another kind of plot that PDP box has, which does the same, but for the prediction. So this is like this, but it's not. It's a different visualization. Instead of using a contour plot, it's using this kind of plot where it's also showing the amount of observations in each kind of subset. So it's good to use this one, and the reason is it can tell you how it's distributed. So one flaw I don't like about this is it doesn't tell you anything about the distribution. And of course, you can kind of account for that using quantiles, but it's a kind of nice to look at the distribution. So we're running out of time. I don't know if we'll have enough to go through the local interpretations. So here we talked a lot about global interpretations, things that we can learn about the entire model. But local is one we want to know about an individual prediction. And so Lime is a very good method for that. So with Lime, we can see pretty much what factored in the decision, the most for one prediction. I won't. There's not enough time, so I won't get into detail of how Lime works. But it's pretty much a linear regression model trained locally to kind of see where the decision boundary is around the prediction in question. And so these coefficients correspond to that, and these coefficients can be read. They can't be understood like, okay, this number means this, but in terms of magnitude, they can be understood. Okay, as if they were weights on one side versus another. And then we're going to quickly go through the SHAP possibilities for local. So this is the bar plot we saw earlier, except where I'm subsetting it by one individual prediction. So here it's telling you why it made it for that prediction. And this is the waterfall plot also for that. So see, it's very similar, the waterfall plot and the bar plot, except kind of waterfall looks more like in a cumulative kind of situation, whereas this is just like, okay, what's on one side, what's on another. And this kind of adds everything up and so says, okay, if I start here, this goes in this direction, this goes in that direction, this is another, and so forth, and then you end up here, right? So that's how the local waterfall. I prefer this one to the bar plot. It's a very similar scenario than the force plots, where you see how many forces are going in one direction and how many forces in another. So it's like the features are fighting against each other to make that prediction. Decision plots, kind of the same situation, except these lines, it's like if you took the waterfall plot and you made everything in two lines. So it's pretty much the same concept. The advantage is you can see multiple features at once, observations at once. So here I'm saying, okay, let's take 16 to 29 and highlight 29. So this one that you see with the dotted lines is 29. And here I can see that one individually. So, right? Beautiful. So I kind of rushed through local interpretation methods. I'm sorry about that, but I was
Yes.
running out of time.
Sorry to
So
interrupt, I guess, Serge, we are running short of time. So
yeah,
we can
I'm
pick
done
up
actually.
to the Q&A section. Yes, and before we get to Q&A section, I have some polls to for our attendees, and I request everyone to participate in this so that we can conduct such more sessions with you all. So kindly participate. I'm sharing the poll here.
Yeah. Um, so let me look at the questions. Um, uh, okay, someone is asking about individual step pre-process. Okay, that's this library called folk tables has the step pre-process, and this is just the step they have to pre-process the data. You can choose not to use it, but it's part of their library. So I'm using it already. Um, I could have used all their pre-processing, but I wanted to do things, like this. To me, it made no sense to make an unemployment classifier with people under 16. It just made no sense. So I took those matters into my own hands. Um, so hopefully I already answered this question. What are you making here? Okay, I think I've already answered what we were trying to do. Which algorithm is easier to explain? MLP, CatBoost, XGBoost. Uh, they're all hard, honestly. Some would think because CatBoost and XGBoost are based on decision trees, they're easy to explain. But generally, like most cases, people when they do CatBoost or XGBoost, they're doing you know, they're leaving it up to as many tree depth as possible. Here we're limiting things to 3 or 4 or 5, but tree depth is how deep the tree goes, and generally if it's a large amount of depth, it's something you cannot understand. So as for MLP, it's also the way the math works in MLP. You could try to explain every coefficient, but it's going to be really hard. Um, so yeah, I don't think I think they're equally hard. I mean, strike that. I think you could. There's something you could do to cap boost and XG boost to make them understandable, which is extract the rules. If you can extract the rules from CatBoost or XGBoost, like was done by rule fit model, you can probably explain them a lot better than you could on MLP. Um, what is MCC in performance measures? That's called the Matthews correlation coefficient. I have it here. Um, I didn't know I had it here. Maybe I did. Oh, I did. Ooh, yeah. A Matthews correlation coefficient. It's actually a very nuanced way at looking at the performance of a model, because what it's going to take is all parts of the confusion matrix and factor them in to make the determination if it's a good classifier. So it goes from I think 0 to 1. No, yeah, 0 to 1. And so I looked into it. It's a very good way of, if you're not like particularly interested in higher recall or higher precision, it's a very good way to measure overall performance. No, this data set might be available in Kaggle. I don't know, but there's a library can fetch it for you. It's actually publicly available. If you wanted to get it yourself, you can go to the website for the Census Bureau and get it yourself. But this library just makes it easier to kind of grab any year of census data. Um, and all the details for this this data set are in the in the Colab link in the actual notebook. Um, Explainability, that's a very good question. When do you explain a machine learning model? Um, you can you can explain a model in every single step. You know, you can even do it. Say you wanted to understand your data, you could do EDA, which I highly recommend, but you could also fit a model to try to understand what kind of connections they are between the data. It might make things easier. So you could use it even before you're actively creating a model, just to understand things about the data. And we do that all the time in statistics. It's done all the time with all kinds of, after all, there's so many different models that are used in statistics for that very same means, like ANOVA is a model. So we can also do it in production. I mean, it's done through every part of the life cycle. In production, the difference is you're doing local interpretation methods mostly. So you're giving people predictions and you're telling them, this is why I predicted this. You could do that. And you can also do global explanations to kind of understand drift. So you can compare the training SHAP values to the production, SHAP values. And you can see if there's any difference there. Do we have interpretable models for deep learning? Yes, we do. And that's something I did not mention here, but there's one called GamiNet. I highly recommend it. And then ReLU DNN. So GamiNet. Oops. So, and ReLU DNN. So this is GamiNet, and it is an interpretable neural network model. But there's also post hoc interpretability methods for deep learning. So those would be like model agnostic ones, and as well as models, no, there would be model specific ones actually. And you can use, there's a whole bunch of them, integrated gradients, methods like that, um, saliency maps, so on. So I've already answered. Can I use these plots both ML and DL? I don't know what plots you're referring to. Um, are you talking about SHAP? You can do SHAP plots for both. There's different kinds of plots, and it's going to depend on your the nature of the data, not so much the model. But like for instance, if you have like a computer vision model, obviously interpreting it is going to be different. To interpret it, every feature is a pixel, for instance. So you're interpreting, how much are each pixel factoring into a prediction or not, or something like that. But for natural language processing, the equivalent to the pixel is the word. So or the token. So it's gonna say, okay, this word in sentiment analysis is the reason why this is regarded as a positive or a negative sentence. Okay. Um, you can't assert causality from a SHAP plot. No, absolutely not. It's correlation. Um, yeah, I don't think I looked into. I think I did put early stopping in the MLP model. Early stopping, yes, it's there. Yeah, you can look into that. You can once it's fitted, you can look into the model and it will tell you at what epoch it ended. But you can make a more complicated model pipeline and so on for neural network, but that wasn't what I was trying to explain here. What I was trying to explain here is like, look at all these models. It will surprise you that MLP wasn't the best one. And that's usually the case for tabular data. It rarely is, to be honest. And when it is, it's overfit and you probably don't want to use it. What's the use of ML in space application or in GIS? Uh, well, that's a very broad topic. ML is used a lot in GIS. I have there's plenty of that where I work, which is with agriculture. Space, there's definitely a lot of ML used in space applications, um, but probably all kinds of optimization methods, even all kinds of mathematical optimization. Um, Yeah, like someone is asking, is there's some debate in the explanations would mean if there's one more factor apart from prediction. Oh, you mean from predictive performance to take in consideration? Yeah, decision making does become hard when you're trying to factor more things. And it's one of the reasons why there's probably friction in this space because people just want simple answers and they want to say, okay, well, I'm going to pick a model based on its overall F1 score and that's it. But once you have to say, well, the F1 score um, has to be well distributed amongst these disadvantaged groups, right? Or also we have to factor that it has to work, it has to be robust, it has to work correctly across all these different years. Then you're complicating the problem, and nobody wants that, but that's how you make a better model. What explainable models are best, state of the art for vision and NLP tasks? Explainable models, as I said earlier, that's a tricky question because I would use more like explainability methods. Like for vision and NLP tasks, generally my go-to is integrated gradients, but I don't stop there. There's plenty of other things. As far as choosing the actual models, it will depend on the use case you have. I tend to think that smaller is better and more specific. So instead of taking like a large language model and for something that doesn't require it, you could train a specific model for what you need. And you'll probably do better in general because you don't know what to find in the large language model. Um, those are only good for like very general purpose things. If you want to throw any kind of question at it in a conversational AI, maybe large language model is the way to go. But sparsity is like one of the key principles of explainability. If you want an explainable model, you have to make things sparse, but also robust. So there's like your training data has to be varied enough for it to be robust, but the features themselves have to be sparse enough for it to be generalizable and in your actual use case. So there's a few other questions.
Okay, so
I think,
sorry to interrupt. I guess we are already running short on time, and either
yeah,
most of the questions they are covered or either they are repetitive. So we can wrap up the session. You can take one last question if there is any, and then we will wrap up the session.
okay. Yeah, I think I did answer most of them. I'm going through them. Um, Presentation, digital. Yeah,
Okay, I
there's a
guess
few that don't seem to apply to me. Like, how do we get a data
yeah,
science internship?
yes,
And if you're
they
going to
are
do
not
Dash,
relatable. Hmm.
um, and then someone asked, what is MCC? I think I already answered that.
Yeah.
Matthew's correlation coefficient. You can look into that. And then, yeah, I
Okay,
won't
so
answer
I
that.
guess
Yeah, I think
all of the
I'm fine.
questions. Yeah.
Yeah.
Okay, I guess all of the questions are covered here. And for our audience, I would suggest if you have any queries, you can check out with our platform, Analytics Vidhya. You will find most of the resources to kickstart your journey in this data science domain. So go and please check out with our blogs for free certifications as well. And so, Serge, thanks a lot on behalf of Analytics Vidya. I would like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it was insightful, and hopefully we can conduct such more sessions with you in the future.
Thank you.
Thanks a lot for your time.